Hello and welcome to this course Machinery Fault Diagnosis and Signal Processing. Today's topic is accelerometer selection criteria and its mounting methods. Now, how do you measure vibrations? Now we know that vibrations can be measured in terms of displacement, in terms of velocity and acceleration. Depending upon the excitation frequency, these vibration measuring parameters are selected. For example, if the rotational speed is very low, then it is recommended to measure the vibration in terms of displacement. If the rotational speed is moderate, then it is recommended to measure the vibration in terms of velocity, and if uh, the rotational frequency is high, then it is always recommended that you measure the vibration in terms of acceleration. So here in today's session we will discuss about the accelerometers and what are the different specifications of the accelerometer that we need to take care while selecting a sensor for vibration analysis, and what are the different mounting methods of acceleration. So that we are going to see in today's session. So vibration is mostly measured by using piezoelectric sensor. Uh, so piezoelectric sensor or piezoelectric material is a smart materials which is made up of ceramic or quartz. Piezoelectric material is a material which generates electric charge when it experiences a force on it. An accelerometer is a sensor that measures the dynamic acceleration of a physical device as a voltage. Accelerometers are full contact transducers typically mounted directly on the high frequency elements such as rolling element bearing, gearboxes or spinning blade. So this piezoelectric accelerometers are contact type of accelerometers uh, wherein this accelerometer has to uh, keep in contact with the surface whose vibration that we are measuring. The benefits of accelerometer includes linearity over a wide frequency range and a large dynamic range. So what is frequency range and what is dynamic range, that we will see in the coming slides. Now what are the different types of accelerometers? Basically they are uh, classified in terms of the output that they are giving. If the accelerometer is giving the output in terms of AC signals, then they are AC accelerometers, and if it is giving in the DC signals, then they are DC accelerometers. So AC accelerometers are examples of AC accelerometers are charge type and IEP accelerometers, and DC accelerometers examples are capacitive, piezoresistive and MEMS accelerometers. Uh, then these AC accelerometers are further classified as charge accelerometer sensors and IEP accelerometer sensors. We know that the sensors are divided as classified as active sensors and passive sensors. So active sensors are those sensors which requires external power source, whereas the passive sensor doesn't require any external power source. So here these AC accelerometers are also classified as charge accelerometer sensors and IEP accelerometer sensors. Basically these charge accelerometer sensors and IEP accelerometers, we will see the details about these sensors in the coming slide. But one thing you remember, that charge accelerometers are passive sensors, that means it doesn't require any external power source, whereas IEP sensors requires external power source. Now what is the difference between this charge type piezoelectric accelerometers and IEP, or sometimes it is also called as ICP or sometimes it is called as deltatron or piezotron. So all these names are synonyms. So ICP, IEP, deltatron, piezotron, so all these are IEP type accelerometers where external power source is required. Now if you compare the charge type and IEP type accelerometers, then in charge type accelerometers, uh, external power source is required, okay, whereas the output from the charge accelerometers has to be given to the charge amplifiers, okay. So in charge piezoelectric, we do not require external power source, but the signals which are coming from the charge type piezoelectric accelerometers are extremely weak, and that is why an external charge amplifiers are required uh, in charge type piezoelectric accelerometers, whereas in IEP or ICP type sensors the charge amplifiers are inbuilt in the accelerometer itself, okay, and that is why to give the power supply to this charge amplifier, an external power source is required, and that is the reason why ICP sensors require external power supply, whereas in charge piezoelectric uh, the the signal is amplified uh, out of the sensor, external to the sensor, and that is why no power supply is required. So this is basically a difference between charge type piezoelectric accelerometers and IEP type accelerometers. Nowadays IEP type accelerometers uh, are popularly used because of the output which IEP gives. So if you see the construction of accelerometers, then this accelerometer is an example of single degree of freedom system, damped single degree of freedom system, in which there is a mass, there is a stiffness element, damping element, and it has got its own uh, damp natural frequency, and we know that the damp natural frequency of a single degree of freedom system is given by omega n under root 1 minus zeta square, where zeta is the damping ratio, okay, and omega n is the natural frequency which is given by under root k by m. So this is the internal construction of IEP type accelerometer. So here a mass is suspended with a preload bolt, and in between mass there is a piezoelectric material, and whenever this preloaded bolt comes in contact with the vibrating surface, it exerts the force on the piezoelectric material, and because of the characteristics of piezoelectric material, it converts that force into a charge, and that charge has been given to the charge amplifiers, which is inbuilt present in the IEP type accelerometers, and then these charge amplifiers amplifies the signal and gives the output for further measurement. Then what are the accelerometer selection parameters? So what are those specifications which every vibration analyzer has to take care? So first is sensitivity. So sensitivity is one of the most important parameter of accelerometer. Sensitivity is specified in millivolt per G. So the unit of sensitivity is millivolt per G, where this G stands for the acceleration due to gravity, and we know that the acceleration due to gravity is 9.81 meter per second square. So if a typical accelerometer sensitivity is 100 millivolt per G, that means for every 9.81 meter per second square, it gives the output as 100 millivolts. So that is the meaning of this sensitivity. So higher the amount of millivolt, higher will be the sensitivity. So in general, use a low sensitivity accelerometer to measure high amplitude signals, and high sensitivity accelerometers to measure low amplitude signals. This graph indicates that the sensitivity is constant for the period of 20 hertz to somewhere 10,000 hertz, 10 kilohertz. So from 20 hertz to 10,000 hertz, the sensitivity is constant, and after that, because of the resonance condition or at the resonance frequency, the sensitivity is quite high. Okay, so this 20 hertz to 10,000 hertz, this is the measurable frequency of the accelerometer. The next is bandwidth or the frequency range. So we have seen that in the previous graph that the frequency measurement range is from 20 hertz to 10,000 hertz, and the measuring frequency should be away from the resonance frequency of the accelerometer. Every accelerometer has got its own natural frequency, and measuring frequency should be far away from the resonance frequency of the accelerometer. So this is the upper bandwidth of the sensor. Small mass accelerometers can provide a resonant frequency up to 180 kilohertz, but for somewhat larger, higher output general purpose accelerometer, the resonant frequencies of 20 to 30 kilohertz are typical. So these are the resonant frequencies of the accelerometer, and the frequency range should be very less than those resonant frequencies. Then next is dynamic range or dynamic amplitude range. So dynamic range is plus minus maximum amplitude that the accelerometer can measure before distorting or clipping the output signal, typically specified in G's, that is acceleration due to gravity. So what are the maximum limit of amplitude which a sensor can measure is termed as dynamic range or dynamic amplitude range. So typically for charge sensors, the dynamic range is up to 1 lakh G, that means 1 lakh into 9.81 meter per second square. But for IEP sensors, the maximum amplitude is 1000 G. Then next is resonance frequency, that we have already seen that every sensor is an example of single degree of freedom system which has got its mass, stiffness, damping element, and they have got their own damped natural frequency. So so designer or analyzer must know what is the natural frequency of the accelerometer, and the measuring frequency should be far away from the resonant frequency. Next we will see what are the mounting methods of the accelerometer. Proper mounting technique is critical for optimal performance. Accelerometer performs So proper mounting is very important. Incorrect accelerometer mounting techniques can result in glossy, inaccurate vibration data, yet accelerometer mounting is often overlooked in the vibration measurement. It's time to pay attention to how you mount your accelerometer. So we will, in the coming few slides, we will be seeing what are the mounting methods of accelerometer and how different mounting methods uh, affects the measuring frequencies. So the typical mounting methods are stud mounted, that is screws or bolts, adhesives, epoxy, wax, tape, then magnetic and handheld. So we'll see these methods in a bit detail. Amplification factor has to be taken care while selecting the mounting method. Accelerometer, piezoelectric in particular, uh, have a very high amplification factor at resonance 2. So it's important to avoid using a mounting method that shifts the resonance into frequency range of your vibration environment. Now here we can see that the resonant frequency are shifted from probe tip to stud type. So as we move from probe tip to pole magnet to flat magnet to adhesive mounting pad to adhesives to stud, the resonant frequencies are shifted towards right. So the highest resonant frequency is in case of stud. So it is always recommend that you mount your sensors by using a stud because it has got highest resonant frequency. So this presents the best mounting method in terms of accelerometer performance and will maximize the frequency response of the accelerometer. It's important to torque the accelerometer down to the manufacturer's specification. So when you mount your accelerometer by using a stud, then a proper torque has to be maintained and a proper greasing has to be maintained, and if you use a proper torque and proper grease, then your resonant frequencies can be kept at a higher frequency level. So that is it is always recommended to follow the manufacturer's instructions. Then next type is adhesive type. So there are several different adhesives to consider when mounting your accelerometers. Surprisingly though, the most important parameter for accelerometer performance is not the adhesive type, rather it's the thickness of the adhesive that plays the largest role. So figure illustrates what little difference there is. So here we can see the different adhesives that we are using, such as tape or Loctite or Epoxy. So different adhesive methods are used, but the resonant frequencies are more or less same. So here the thickness of the adhesive plays very important role. So the thickness of the adhesive has to be selected properly. So Loctite or Epoxy are types of adhesives. So wax or duct seal, putty are also adhesives. Then double-sided tapes are used. Magnetic mounting base. So this is also very interesting mounting method. For ferrous magnetic structures, a magnetic mounting base allows easy and mess-free accelerometer mountings. So there are two types of magnetic bases, flat and curved. Flat offers the best frequency response. You should use caution with the magnetic mounting base. Do not damage your structure or injure yourself, but there are a great solution for short-term testing applications. So here are some accelerometer magnetic mounting bases from PCB. So magnetic mounting bases are also very handy. We can take out the accelerometer and put the accelerometer with lot of ease. Then there are handheld or prop tip accelerometers. So some applications can be different to reach for a proper mounting or have a sensitive coating or material that prevent adhesives or bolting. So a probe tip can be utilized to press the accelerometer to the structure by hand. This obviously drastically reduces the measurable frequency range to less than 10,000 Hertz. So if you are measuring the vibration for less than 100 Hertz, then it is recommended to use the handheld probe. Otherwise, more than 100 Hertz frequency measurement, it is recommended to use either of the above mentioned methods, because humans can't remain perfectly still either. They are not recommended from the frequency range is less than 10 Hertz. So the conclusion that we can draw from the discussion is the mass of the accelerometer should be significantly smaller than the mass of the system to be mentioned. The accelerometer dynamic range should be broader than the expected vibration amplitude range of the sample. The frequency range of the accelerometer should fit the expected frequency range. The sensitivity of the accelerometer should produce an electrical output compatible with the existing instrument, and use a low sensitivity accelerometer to measure high amplitude vibration, and conversely use the high sensitivity accelerometers to measure low amplitude vibrations. Okay, so this is all about the accelerometer specifications and their mounting methods. So thank you very much.